Okay, so what we want to show that 1 over t is ds by dE. And this actually comes directly from the first law of thermodynamics. So let's see why that is. So let's start with the first law and let's write it in its most familiar form. So you'll have seen du equals dq plus dw, which is t ds minus p dv. Okay, so that's how you're used to seeing the first law. So because we're dealing with the microcanonical ensemble, dV equals 0, so the volume of the system is fixed. So PdV must be 0, so we can say that du is equal to T ds. But in statistical mechanics, instead of U, we normally write E. So we're going to write dE is T ds. So it's exactly the same. It's just that I tend to use E in statistical mechanics rather than U. And then we can say that d1 over t is ds by dE. Okay, so that's the first step. Now we want to try and calculate this thing here, ds by dE. So let's think about what we know. Well, we know the energy of one of these Schottky defects. We need that E is little n epsilon. And we also know the entropy associated with a Schottky defect because we counted that. So we know this thing, S of n, which I'm not going to write the whole thing out all the time because it's a bit long. Okay, so what we need to do is we need to use these quantities somehow to calculate this derivative. So let's take this thing here and see what we can do with it. So we can do 1 over t, and we can do this little mathematical trick. We can say that this is ds by dn times dn by dE. Okay, so now we can definitely calculate this term because we know that E is n little e or epsilon. So we can write dE equals the energy associated with each defect, which is of course a constant, times dn. So we know that dn by dE is 1 over epsilon. So we can then say, that 1 over t is equal to, so we've got a ds by dn times a dn by dE. So we'll do the 1 over e ds by dn. Okay, so now all we need to do is evaluate ds by dn. So this is what we worked out before. So I'm going to write the whole thing out. So S, which is of course a function of little n, the number of defects, is Boltzmann's constant K. Then remember, this is the thing that we worked out from Stirling's formula. So we have n ln n minus little n ln little n n ln n minus little n. That should be curly brackets, and that should be a straight bracket. So this is just the result that we calculated last time. And now what we're going to want to do is we're going to want to differentiate it with respect to n. So find ds by dn. Okay, so what we want is we want d by dn of n ln n minus little n Okay, so that's what we want to evaluate. So let's try it term by term. So d by dn of n ln n, well, that's 0, so we can get rid of that one. Now we want d by dn of little n ln little n. So, okay, let's use the product rule. So let's differentiate n, which is 1, and keep ln n constant. So that's ln n. Plus, then we're going to keep this one, so n times, and differentiate this, which is the derivative of log is 1 over, times 1 over n. So we get ln little n plus 1. So that's that term. Okay, now we want to do this term here. So d by dn of minus little n and then n minus little n is equal to. Right, okay, so let's differentiate this term first and keep this one constant. So we're going to differentiate this, so we're going to get a minus 1. So we end up with minus ln n minus n. And now we want to keep this term constant and differentiate this one. So we've got plus. Now we've got an n minus little n. And differentiate this. So we get a 1 over n minus little n. But when we differentiate the thing inside the bracket, we get a minus 1. So that's times minus 1. So this gives us minus ln n minus little n minus 1. Okay, so now we can collect all of the terms together. So ds by dn is equal to, and because we're dealing with the entropy, we'll be careful and we'll put our Boltzmann constant back in. So we've got k. So the first term was 0. Differentiating this gave us 0, so that's okay. Differentiating n little n l little n gave us an ln little n plus 1. Then differentiating this thing, but we've got to remember this is a minus, so let's put a minus in there. And we've got a minus here for whatever we differentiated here, which was minus ln n minus 1. Okay, so let's sort out all of these minus signs. There's something is bound to have gone wrong here, right? Okay, so that's k, that's minus ln n minus 1 plus ln big N minus little n plus 1, which is k. These go out and we end up with ln big N minus little n minus ln n. Which I think is correct. Okay, so we've done all of our differentiation. And now we can put our two terms back together to find out what our temperature dependence is. So let's just remind ourselves what we did. We had 1 over T is equal to ds by dE. And then we did this trick where we said 1 over T was equal to ds by dE, which is equal to ds by dn, dm by dE, and we had the n by dE we got as 1 over epsilon. And the s by dn we have just calculated, which was k ln n minus little n minus ln little n. Okay, so we know that 1 over T is equal to K over epsilon ln of, now because this is ln n minus little n minus ln of little n, we can write that, because of the beautiful power of logs, which we enjoy so much, m minus n over little n. Let's put all those brackets around. So what we have here is quite exciting, because what we have, let's just make sure that that looks like Boltzmann's constant there. So what we have is we have an expression for, so we've got temperature here, we've got the energy associated with each of our defects here, and then we've got the number of defects and the number of atoms in the lattice. So what we have is we have a relationship between temperature, energy, and the number of defects. So we can now say at a particular temperature how many defects there are. So I'm going to rearrange this, and I'm hoping that you'll start to recognize some of the expressions that emerge from this. Okay, so let's just tidy it up a bit. So let's take the e's and the k's over to this side. So we've got epsilon over kt is equal to the log of n minus n over little n. And of course, we can take the exponential of both sides. So we get e to the epsilon over kt equals n minus little n over little n. And we can write that as big N over little n minus 1. And then we can take the 1 over to this side. And this is good because we've got this thing big N over little n. And if we flip that over, that's going to give us the number density of defects. Because remember, big N is the number of atoms in the crystal and little n is the number of defects. So little n over big N is the number density of defects. And that sounds like a useful thing to be able to calculate. Okay, so let's just tidy it up a bit. So we have, again, e to the little epsilon over kt plus 1 is equal to our upside down number density. So if we flip it upside down, take 1 over it, we end up with little n over big N. Our number density equals 1 over 1 plus e to the epsilon over kt. Fantastic. Now, let's think about a situation where this term here, this exponential term, is far, far bigger than 1. And this is going to be the case whenever epsilon is very much bigger than kt. So if we take that limit, let's think about what happens. So we're saying that little epsilon is bigger than kt. So we're in this limit. And this means basically that the energy needed to create a defect is bigger than the thermal energy. It's much bigger than the thermal energy. So if that's the case, then of course this term here, the exponential term, is absolutely humongously massive. And if that exponential term is humongously massive, then we could ignore this one here. So within this limit, we can say little n over big N is approximately equal to e to the minus epsilon over kt. As if by magic, the Boltzmann factor point pops out. And so I hope you guys think that this looks a little bit familiar at least. So this is the very, very famous Boltzmann factor that gives you the probability that a system has a particular energy E, in this case, little epsilon. And so, of course, for our Schottky defects, the probability, the number density of these, the probability of one occurring, is given by this exponential Boltzmann factor. So in order to get this, let's just recap. What we did was we used our first law to write down the relationship between the temperature, the entropy and the energy in the microcanonical ensemble where the volume's constant. We could do our little mathematical trick to change variables so that we could evaluate what ds by dE is. And we could do that because we'd defined what the energy was in terms of the number of defects. And we also knew the entropy as a function of the number of defects. So we could then evaluate this derivative. Then here's the derivative. So we work through this algebra. We could rearrange this derivative to write it in terms of the previous expression we had for 1 over t. So this is where we've substituted into our ds by dE that we got from the first law. And then we were able to solve for the number density of defects, little n over big N. And we get something that looks fabulously like the Boltzmann factor. So this is really, really cool because what we've been able to do is having a knowledge literally just of the energy associated with one of these defects, we've been able to use the machinery of statistical mechanics to calculate the probability that we will see a defect as a function of temperature. So let's just have a look at a few of these numbers. So typically an energy associated with one of these defects will be about an electron volt. So have a go and work out what kT is, Boltzmann's constant times the temperature, what KT is in electron volts. That's a very useful thing to be able to do. So do have a go. And I got that at 290K, KT was about a 40th of an electron volt. So we can calculate our number density of defects. So little n over big N is about e to the minus 40. That's quite small, only about 10 to the minus 18. So, but, you know, we'd see one in a mole, right? So it's small, but it's not unbelievable. You know, these defects will still exist because in a typical crystal, N is so large. So what is the concentration when T is 1,000 Kelvin? So exactly the same calculation, but we get a far bigger number because, of course, we're at higher temperature, so there are more and more defects produced. This is a general result, and it is absolutely everywhere. It's ubiquitous. I mean, it forms the foundation of the partition function, which we'll talk in the next lecture. But it's impossible for me to overemphasize how important this concept is. That if you have a statistical system, the probability that your system has an energy E in statistical mechanics is proportional to the exponential of minus that energy over KT. So let's just have a look and a bit of a think about what this means physically. So E is the energy that your system needs to have, that it's trying to acquire. And KT is the sort of ambient thermal energy that's kicking around at the time. So if the energy that you're trying to achieve is loads bigger than the thermal energy KT, then this probability is very small, because you've got an exponential, which is a really macho function, an exponential raised to the power of minus EI over KT. So if this is a lot bigger than this, then e to the minus that number is going to be small. So that means that if you're asking a system to have an energy, or you want to know the probability that the system has an energy that's far higher than KT, Boltzmann's constant times the temperature, the amount of thermal energy sort of kicking around in general to do things, then it's really not going to happen very often. But states where KT and E are comparable, those crop up all of the time. So this exponential factor is known as the Boltzmann factor, or the canonical distribution function. It is absolutely ubiquitously everywhere. So I hope that you've enjoyed it.